Okay. I've been waiting for you to ask this question, actually. No, I'm just kidding. But I pulled it up anyways, so we could do it together, because I haven't done it yet. And I have like a vague understanding of it. And I haven't finished reading chapter 17, but it's been making things a lot clearer. So the first thing we're going to want to know for this exam is the Nernst equation. And the Nernst equation is the cell potential, or E of the cell, is equal to the E of the cell in standard conditions minus RT, which is the gas constant times temperature, over N, or this is sometimes written out as Z, and times Faraday's constant. And then this is usually a natural log of Q. So this is the full Nernst equation. Most of the time, when we're answering these questions, I think almost all of the time actually, we're rearranging this entire equation over and over and over again. And if you get curious and you want to get better at it for things beyond the exam for whatever reason, you can play around with these and rearrange it a little bit. See like how it would look if you want to get this, how it would look if you want to change the natural log to like the basic version of the question to the is it the natural logarithm? Hold on. It is the log base. So you go from the natural log to the log base. And you do that by like you do all of this r times t over f, all constants, and you multiply it by 2.303, and then you get the log. We're probably going to be supplied the equation with log instead. So it's going to actually look like this, maybe E of the cell minus, I think 0.5, 0.05, I don't know, 9, is it 916? 0.05916 over N, and then log of Q. And then in this question, a couple things we're going to want to try to pull out from the question as soon as we read it is, what is it asking for? This one is saying, for the following reaction, generate an equilibrium. That's the key word here. Constant. Equilibrium constant expression, and calculate the numerical value for K of the equation, or the constant for the equation. Assume that H plus is equal to 1 mole. Given the following reduction potentials. Hint. Balance the equation first. So some things we want to kind of like immediately pull out is like if it's asking for equilibrium constant, if it's asking for cell potential, because these are a little bit different and they'll vary, but it's all based off the Nernst equation. So because this one is asking for the equilibrium constant, we're going to assume that the cell is in standard condition. And so that means we're going to assume that the temperature is at 25 degrees Celsius, which is 298 degrees Kelvin. And then the gas constant we're going to use is 8.314. You can add the units if you'd like. I always forget, but I think it's like joules times something over moles times Kelvin or something like that. Times mole, I think. And then the temperature is going to be 298 Kelvin. Okay. But we're going to use the simplified version, which already multiplies these constants in. And then something else we want to know is, remember what Q was, the reaction quotient, and remember what K was, is like the equilibrium constant. And if Q was like bigger than K, it's going in one direction. If it's smaller than K, it's going one direction. However, if Q is equal to K, that means it's at equilibrium. And so that's why we're going to take this Nernst equation and we're going to swap out Q for K. And we're going to find K, because we're going to assume that this is at equilibrium. Okay. And then we're also going to, when a reaction's at equilibrium, E of the cell is going to be equal to 0. And chapter 17 explains this a little bit better. But because E of the cell is equal to 0, now we're going to rearrange this around to get this number to be up front. So this, we're going to just write down our formulas just to get comfortable with it. E of the cell is going to be equal to, when we rearrange the entire thing, it's going to be like 0.05916 over n, and then log of q. Like that, I think, right? And then, and this is assuming that these standard conditions. And then we're going to try to now balance this reaction and find E of the cell. Because, whoops, not Q, sorry. Okay, remember, we're at equilibrium. So to balance this reaction, we're going to do the first step, which is to separate them into each of its own half reactions. So we have Be2032 minus is going to be, oh, don't forget your states, Be solid. And then the other one over here is Tas2 Ta2O5 aqueous. Okay, that's the first step. Second step, we're going to balance everything that is not oxygen or hydrogen. So this is going to need to be 2. So we're going to have Be2O3 2 minus aqueous to 2 Be solid. And this one's going to also be 2 Ta solids. There we go. Then we're going to start to balance our oxygens. And we're going to balance the oxygens by adding, we're also all this balancing stuff, we're only going to assume acidic medium. So that means it's going to be 7 steps. He's not going to have anything to do with basic on the test, but even if it was basic, we would balance it, do all that stuff, and then it would, then the 8th step is just like adding OH to both sides. But we're not doing that. We're just going to do the 7 steps. So it's going to be oxygen, then we're going to balance hydrogens, then we're going to balance the electrons. So next is oxygen. So there's 3 oxygens on this side, so we're going to add 3 H2O to this side. So it's going to look like this. Good. This one has 5 oxygens on this side, so we're going to add 5 H2Os to the reactant side. We do like a little split here. Okay, now we're going to balance the hydrogens. So we have 6 hydrogens on this side, so we're going to add, we're going to balance it by adding H plus, or protons, or hydrogens. So we're going to add 6 of these. I think this one's also aqueous. This is the part I always mess up on, because I always forget to carry everything down and to keep it going. And it's like nice to keep track of it this way too. Okay, we did it that side. This side, there's 10 hydrogens, so we're going to add 10 protons onto the right side, or the product side. Now we're going to add, we're going to add electrons to the sides that need it. So first we have to calculate what the charge is on both sides. So this side has a charge of like 0, I think it is. Right, I didn't forget anything, yep. And then this side has 6 plus minus 2, so 4 plus. So that means we're going to get down to 0, we're going to add 4 electrons to this side. So this is getting intense. It's like getting smaller and smaller. I could have just like written it on that side, but it's okay. Okay. Now that we added 4 electrons, they should both be at a charge of 0, both sides. Let's do this side. This side has no charge. This side has a charge of 10 plus. So this side, we're just going to add now 10 electrons to the product side to get it down to 0 charge, because right now it's at 10 plus. Oh, barely made the cut. And now step number 6 is usually to try to get the electrons equal to each other. So you can like multiply this side by 4 and like this side by 10 and get like 40 electrons. Or there's like another way of doing it that's a little bit easier. Okay, which is like if you, so that way you don't have to simplify later on. If you multiply for this entire side by 5, you'll get to 20 electrons. And then if you multiply this entire side by 2, you'll get to 20 electrons. So we want both half reactions to have the same amount of electrons. And we're going to do that by multiplying this entire one by 5, this entire one by 2. That's going to be our step 6. Let me draw it out here so I have more space. So everything multiplied by 5, 4 becomes 20 electrons plus 30 protons plus 5 Be2 O32 minus plus 10 BeS plus 15 H2O. Whew. Okay, step 6 on this side is it's all going to just be multiplied by 2. Okay. Then we add everything together. Step 7 is just adding it all to make like one continuous equation, which is going to include canceling things on both sides. So if we look at everything we have on the reactant side here, well, automatically we're going to check to see where our electrons are. My electrons are on the product side on this side and the reactant side on this side, which is a good sign. It means we did something right. So these are going to cancel out when you add them together. And then same thing with the protons. We have 30 here, 20 here. That means all 20 here are going to be taken out or like matched up and crossed off. And there's only going to be 10 remaining here. Then let's look and see if there's anything else matching. Nope. Ooh, H2O is matching here. We have it in the reactant side here and the product side here. That means we can cancel out 10 of these because there's 10 on both sides. So all of the 10 on this side cancel out, and then there's going to be 5 left over here. Then we're going to add it all together, so it's like one straight reaction. So we're going to have 10 protons plus 5 Be2 O32 minus 10 BeS. Oh, I made it. Oopsies. I didn't finish adding all my reactants. So I have my protons, I have this side of it, and now it's done. I'm at the arrow. I'm going to get everything before this arrow on this side, which is this thing I left out. Then we add our arrow. Then we can add the things on the product side for this half reaction. That's L. And then we can add, we're done with that one, all the ones on this side for this half reaction, which is just 2Ta2O5 aqueous. Ta-da! And we did all of this so we can get, we actually didn't need to do this step, honestly, because we had our moles of electrons, which is 20. But this is good, because if we get a question on the exam where we have to get to this step eventually, you know how it's supposed to look and how you're supposed to cancel out. So that was kind of helpful, right, for practice. But we have 20, so we have our N, and And then, so usually with E of the cell, E of the cell is going to be equal to your reduction, or your cathode, minus your oxidation, or your anode. And usually the higher voltage is going to be your reduction, or your cathode, and the lower voltage is going to be your anode. And you can, after balancing it all out, you can still double check to make sure that it's right. And you do this by checking. So like I'm going to check for barium here. It's going from 2 minus to 0, so it's being oxidized. This one's going from 0 to -2, 10, and then 2 of these to positive 5. Is it positive 5? No. This is 0. -2 times 5 is -10. It's neutral, so that means this is positive 5. Yeah, so this one's going from 0 to positive 5. This one's being oxidized. So why is it the reduction? Oh no! See, this is why we have to balance it out. Silly me. It's down here. So you're going from 0 here. You're still going from 0 to positive 5. I don't know why this is. I'm assuming this is the cathode because it's the higher voltage. Reduction. And then this one, oh, it might actually be this one, because this has a charge of 2 minus. -2 times 3, we have the -6 here. Then we have the 2 bariums here. But it would still be +2 to 0. Oh, this one's being reduced. So actually, this is the reducing one. This is the reduction, and this is the oxidation. Oops, why did I put a 0? Because in the balanced equation, this is going from +2 to 0. Yeah, and this one's going from 0 to +5. So this one's being oxidized, and this one's being reduced. So when we set this now to get E of the cell, we're going to put E of the cell is equal to -2.63 V minus -0.75 V. There we go. Now we're going to get E of the cell. Let me do it real quick on my calculator. It's -2.63 minus -0.75. And then our E of the cell is equal to -1.88. Nice. So now we have our E of the cell, we have our N, and we have our constants here. And so now all we have left is to do is to find K. And now this is just like algebra. Just set it up so that K is on one side of the equation, or log K is on one side of the equation. So we're going to write it down. We're going to write our E of the cell is equal to 0.05916 over our mole of electrons, which is 20, and then log of K. We're going to find log. So we're going to do, we want to get this entire thing out of here. So the first thing we're going to do, what he does in class is like he shows us how to cross multiply. But because there's the equal sign here, it gets me a little confused. So I just do it like the entire thing is like multiplied by 20 on this side. That gets erased. Then this entire thing is multiplied by 20. So this times 20 is equal to -37.6. And now that this is gone, we still have this multiplied attached to this by multiplication. So we divide this entire side by 0.05916. Then I divide this side by 0.05916. And that's how I get rid of both of those numbers. 5916 is going to be equal to log K. I'm going to do this really quick over here so it's clear. Okay. Is this supposed to be that big bad number? Times 20 divided by 0.05916. So now I have -635 0.56, what a big number, is equal to log k. And now to get rid of log, you write 10 to the log to get rid of that, and then 10 to the negative 635.56. Your calculator, I don't think, is going to give you an answer for this. So then this becomes 10 to the negative 635.56 is equal to k. So this is your answer. I think I remember doing this in class and it did not give us a number because it's too big and it's going to give me like an error message. Or it'll say 0. In some calculators it gives you an error message, but it is not 0. It's just a really small number. But it'll give you 0. But he said if you write it and leave it as this, he will still give you full credit. And that's how you do this question.